Hello, I welcome you all to this another interesting screencast. We are going to be solving this engineering mechanics problem, and it reads, determine the moment of inertia of a beam's cross-sectional area with respect to the x prime centroidal axis. Neglect the size of all the rivet heads R for the calculation. Handbook values for the area, moment of inertia, and location of centroid C of one of the angles are listed in the figure. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. We have a real cross-section of a beam, and we are being asked to find the moment of inertia of an area, also called area moment of inertia, and it is also called second moment of area. And this is a geometric property of a shape such as the cross-section of a beam, which describes how the area is distributed around an axis. An axis where we want to find moment of inertia of an area. Mathematically, moment of inertia about the x-axis is defined as I sub x equals integral of y squared dA, and moment of inertia about the y-axis is defined as I sub y equals integral of x squared dA. It has several uses, among them, in science and engineering disciplines. Within engineering discipline, if I was to just pick one discipline, which is mechanical and structural engineering, we use it for calculation of deflections of beams, for buckling load calculations of column, and so many other applications. All right, let's dive into the problem. So this is a composite beam. This is a composite beam because it is made out of a number of elements. Okay, so we have this top part, okay, which is a cross section. Okay, the beam itself, if we are to look at this beam, okay, it looks something like that. Okay, that is how the beam itself would look. Okay, all right, so that is how the beam would look if we were to look at it. But what we are looking at right now is just a cross section. This is an I beam, letter I beam. Okay, so we have the top part here, which is also called the flange. Okay, we have the flange, all right, and the flange is connected to this other element here, which we can call as a web. Okay, so this is a web. All right, this is a web in green, and this web is connected to the flange using these angle bars. You can think of these as angle bars or angle beams. These ones I'm drawing in blue. Okay, these are the ones that are connecting the two elements together, the flange and the web, and they are being connected using rivets. Okay, and then later on we come up with a composite I-beam. So now we are being asked to find the moment of inertia about the x prime axis. And when we look at this x prime axis, this just looking at it, it is the centroidal axis of this composite cross-section area. Okay, it is passing through the centroid of this composite cross-section area of this beam. Okay, so for the angle bars, they've already given us the geometric properties, which are the area and the moment of inertia about its centroidal axis, centroidal x-axis. Okay, and there are 4 angle bars. All right, there are 4 angle bars. This one, they've given us these values. They've given us moment of inertia and area is just for a single angle bar, angle bar. So when we start calculating, we need to remember to say there are 4. So we need to be multiplying by 4 every time. When you calculate the area for the angle bars by 4, moment of inertia by 4. For the webs, there are 2 of them at the top and the bottom. I mean the flange. The flange, there are 2 of them. Okay. We have the flange on top and we have the flange at the bottom. Then we have just one web, of course. So let's assign this particular cross-section the geometric properties. So before we do so, let's name the shapes. Okay, so this is how I'm going to define them. For the flange, this one in red, where does it pass? Down there. For the flange, this one in red that I'm outlining, this will be my part 1. Okay, and then the one in green, I mean the web is going to be in blue. I mean the angle bar. The angle bar is going to be my part 2. Okay. This one is going to be my part 2. And then finally, the web is my part 3. The one I'm outlining in green. Okay. Great. So we have part 1. We have part 1. Then we have part 2. And then we have finally part 3. Alright, is that fine? Great. So there we go. So about the centroid about the x prime axis, this is where we want to find moment of inertia, right? So let's start with part 1. We draw at the very middle, part 1 like so, something like so. Okay. And then I extend this one, just something like that. Alright, this is fine. And then we go to part 2, which is the angle bar. Angle bar, I'll just draw a line there. This is fine. And then this is about it, right? The other one, it has for the web, the centroidal axis, I mean the y component, the y curved bar in the y direction is 0. Okay. So this is about it. Let me just work on this a little bit. Great. I think it's about it. So let's name this. So this one is our y curved 2, 1. So y curved 1 and is equal to the length of the whole web is 275, therefore half of the web, then minus, plus, not minus, plus half of the thickness of the flange, which is a 20 divided by 2. Then this gives us a 147.5, right? 275 divided by 2 plus 20 divided by 2. And then this one this is y curved This is YKL2 is equal to half the length of the web, which is 275 divided by 2, and then minus 28, right? You've seen this 28? Okay. So this is equal to, so 275 divided by 2 minus 28. This is 109.5. Great. What else? And then Y3, YKL3 is just equal to 0. Great. So let's find the area. Area 1, that is the area for the flange, right? There are 2 of them, so it's 2 times 2LB, which is equal to 2 times, what is our L? What's our L? Our L is 75, and our height, our B is 20. Therefore, this gives us a 3000, right? I'll write it the way they wrote the area for this scientific notation. So 75 by 20 by 2, that's a 3000. It's a 3000. So I'll write it as 3 to the power 10, 3. Okay. Area 2, this is the angle bar. They've already given us is equal to area A, which is equal to, how many are there? There are 4, so it is 4 times 1.36 times 10 to the power 3, which gives us, what does it give us? That's 1.36 times 4. So this gives us 5.44 to the power 10, 3. 10 to the power 3. Then area 3, it is the web. It's just a single one, L times B, which is just equal to 15 times 275, right? Of course. 15 times 275, this gives us just a 4.125 times 10 to the power 3. Okay, I just maintain the way they wrote, or they indicated the area for the angle bars. Okay, so let's now find the centroidal moment of inertia. Ix1 equal to, what is it? What is our moment of inertia? Let me just move this a little bit behind, like so. Okay, so I1, what we have, I1 is the flange, which is just a rectangle, and there are 2 of them, so I'll just say 2 times 2 divided by 12 BH cubed. They'll have the same moment of inertia about the x prime axis. That's no, they will have the same, rather, they will have the same, yes, they will have, but the centroidal moments also, they are going to be the same. These are the centroidal moments, so this is going to be equal to 2 divided by 12. Our B is 75, and our H is 20 to the power 3. So what does this one give us? This is 75 by 20 to the power 3 divided by 6. Okay, divided by 6. So this becomes a 0.1 1 10 to the power 6. Okay. And then what do we have? We have moment of inertia for the angle bar, which is just IA, is equal to, like this one here, it is supposed to be 4A. Let me write a 4 there, A, like so. So this is going to be equal to 4IA, which is equal to 4 times 1.32 10 to the power 6, which just gives us a 5.28 10 to the power 6. Okay, is that so? Of course. And then finally, moment of inertia of the wave will just be h cubed divided by 12, and this is equal to, our b is 15, our h is 275 to the power 3 divided by 12. This gives us 275 cubed by 15 divided by 12. Okay, so this one is a 25.996 times 10 to the power 6. Okay, so this is about it, right? This is about it. So what we need to do now is to just draw a table, because we're just finding moment of inertia about the x prime. Okay, so we have everything, so let's draw the table. So we have part, then we have moment of inertia centroidal about the x-axis, then we have y curled, we have area, then we have y curled squared times area. Okay, mind you, we're using the equation, the parallel axis theorem, moment of inertia about the x-axis, x prime is equal to centroidal moment of inertia plus dy squared times a. Okay, so this is the equation that we are using. All right, so let's draw a table quickly. This is not good enough. Great. This looks cool. So something like that part. There we go. Moment of inertia, area, move area there, move this one there, something like that. Okay, all right, great. How many are there? There are just 3, and then plus C for summation. Okay, this is fine. This is fine. Great. So let's fill it in. Let's fill it in quickly. 1, 2, 3, summation. First moment of inertia, centroidal moment of inertia for the first part, which are the 2 flanges. So we have a 0.1, 10 to the power 6. Second one is 5.28, 10 to the power 6. Third one is 25.996 times 10 to the power 6. Centroidal distances with respect to the x prime axis, y curled 1, we have a 147.5. Mind you, the units are in inches, and moment of inertia is expressed in inches. For here, it will be in inches per power 4. So just, even when I'm not indicating units, I'll indicate units for the final answer. Sorry about that. The second one is 109. Okay. The third one is 0. And then area, what did we find? For the first part, there are two of them, is 3 times 10 to the power 3. Next one is 5.44 times 10 to the power 3, of course. The third one is 4.125 times 10 to the power 3. Alright, let's look at the products. The numbers are a little bit long, I think so. So let's extend that. You can extend it just a little bit up to somewhere there. Okay, great. So there we go. So the product, we have 147.5 squared times 3 times 1000. So this gives us a 65.268 268. Okay, 2688 to the power times 10 to the power 6. Okay, sure. Okay, let me just write the whole lot of it. I think it can fit there. I'll round it off later on. Let me just write everything. So this one is a 65, 268, 750. Next one, 109.5 squared times 5.44 times 1000. This is also 65, 226, 960. Third one is a 0, of course, so let's sum up. 0.1 plus 5.28 plus 25.996. So we have a 31 there, 0.376 times 10 to the power 6. And then that side we have a 65, 268, 750 plus 6522 6960. Okay, so we have a 130.4957 times 10 to the power 6. Okay, so finally let's write down the moment of inertia. Moment of inertia about the x prime is equal to moment of inertia about the centroidal axis plus y cubed squared times area, which gives us a 31.376 times 10 to the power 6 plus 130.4957 times 10 to the power 6. And finally, our moment of inertia is equal to, let's add that, so 31.376 plus 130.4957. So we have a 161.87, okay, times 10 to the power 6, and this is inches to the power 4, right? No, millimeters, sorry. This is in millimeters, right? But why was I talking about inches? This is in millimeters to the power 4. Okay, so this is the final solution. This is the final solution for this particular problem. Of course, you expect the highest moment about the x prime, okay? About the y prime, if this was the y prime, imagine this was the y prime, moment of inertia about that axis would be less compared to the moment of inertia about the x prime, right? So x prime, moment about x prime is higher than moment about the y prime. Okay, I think this is about it. I hope the video was helpful, and if it was, give me a thumbs up, like my video, and continue subscribing and sharing my channel. I'm going to share the other links for the other videos I've done for moment of inertia. Bye bye, and see you in my next task.